one option is that you basically have a gravitational instability, probably already happening in a very early phase of the disk, when the disk mass and the stellar mass are still comparable. But there are also other theories, like that you have a dead zone edge, pebble grows at snowline. So let's say the theorists are not short of suggestions as to what could be happening here. The interesting thing is that we are now starting to see sort of evidence for multiple planets. This is one very nice disk on the southern sky, HD 10546, where we see here our dust disk and our gas disk. And now if you subtract sort of this main dust disk, then you see here an outer dust ring at a level that is only 1% of the peak flux, but that is sitting here just outside where a planet has just been discovered. So this is here a planet inside the disk, young disk, that has been seen by Sasha Kwanzadal using VLT-NACO, and this is sitting here just inside as to where we see sort of this second dust trap here in this particular disk. So this is just to illustrate that there's probably lots more in the making in the coming few years with ALMA, that we're starting to see not just the single dust rings, but more dust rings here where we can have these particle traps, and that's provide us with information on these planets. In this particular case, actually, by modeling the dust evolution, the conclusion from this modeling by Paolo and Catherine Walsh is that the second planet is probably younger than this first planet by about 2.5 million years. So again, we're starting to already make inferences on planets that we cannot see, but that we think are actually there. Okay, so then to end, so far I've been talking mostly about this case, which probably holds for the rings that we've been able to observe so far, the ones with large cavities, larger gaps of, say, tens of AU. In reality, probably a combination of all of these processes plays a role. And you can only start to disentangle that if you have large samples. And just to show you again the power of ALMA, this is recent results from a unbiased survey of all the disks in the Lupus star forming region, some 100 in total. So what we were able to do here is use ALMA just 1 minute per disk in both continuum and in carbon monoxide lines. And that already gave us more sensitivity per disk than any of the previous observatories. And this is a paper that has just appeared on AstroPH. So we basically surveyed all the Tittori stars in Lupus in dust and gas. We detected the majority of them in the continuum, and we detected also a fraction of them in CO. And so we can now really start to do in more detail, put sort of these transitional disks in context with the normal disks and see how the gas and the dust evolves. And in fact, in this particular survey, already with 1 minute of integration time, we started to pick up several new transitional disks that you see here in these objects. So stay tuned for more on the terms of statistics. So I would like to end here. I hope to have shown you that with ALMA, we can really start to probe sort of all of these phases of disk evolution. We can start to probe the formation of disks in the deeply embedded phase. This is also where we have a rich chemistry going. We can really see the initial composition, basically, chemical composition of these forming disks. The structure of the mature disks is being unraveled by ALMA. Snow lines are definitely very important here. And then transitional disks are wonderful targets if you want to study sort of planet formation in action. Thank you very much.
Thanks very much. Questions?
Could you say a little bit more about this idea of planetesimals forming even earlier than what we thought, and what you would expect the distribution, how the evolution of their distribution?
Yeah, well, that's. I wish I could say more about it, except that it's likely that it's happening already. Unfortunately, they have not been able yet to get many high angular resolution images of the young disks. Actually, HL tau is is the only one. But some of these rings that you see may actually be sites where the planetesimals are forming at this moment. It could just be a change in opacity again, rather than a forming planet that you see in this HL tau disk. So that could already be the sign of forming planetesimals. I think you really need to have more than one object in order to get sort of statistics on this. But I mean, there's every possibility also through gravitational instabilities that you can form sort of these clumps already early on.
How do they transit from being a spherical? How do they go? Spherical distribution.
No, they would already be in the forming disk, so they would already be in a flattened structure. So they would already be in the flattened rotational disk. Yes, yes. So it's really inside the rotational, sort of the Keplerian part of the disk, or the near Keplerian part of the disk that they would be forming.
I'm thinking in order to have the planetesimals to add to each other and form a planet, you really need the disk. I mean the ring. Mm-hmm. Otherwise, the meeting of two planetesimals would be extremely violent, and that they would simply destroy each other.
Yes.
So
yes,
I think that there's somehow it's absolutely necessary to form a group that moves more or less at the same velocity and whatever.
Yes. So it's really that you get sort of this ring of planetesimals, because indeed you have in these pressure bumps normally the dust and the gas move at slightly different velocities, and so the dust particles feel this headwind. That's also why their orbits decay and why they move in so quickly, why you have sort of this problem of forming planetesimals quickly enough. So these pressure bumps solve two issues. They solve the radial drift problem, because you basically trap them at a certain location, and they also solve the fragmentation barrier problem, because in a pressure maximum, actually the particles don't have this headwind problem. So that is why they can also grow much more. You have much less fragmentation. So these pressure bumps are really key to many aspects, and so they really need to be included in detail in planet formation and disk evolution models.
So, Ewine, thank you. I have very stupid questions, but I have to ask. Now, the dust becomes separated from the gas. Does the gas migrate outwards, or does it migrate upwards? Does it go inside? Do you have any thoughts about that?
Yeah. So that's so. I should say the millimeter dust doesn't move as the gas. So it really depends on the size of the dust particles. So there's this so-called Stokes number, where at Stokes number equals 1, basically is when they start to just decouple from the gas. So the very small dust particles, the submicron size, they still remain coupled to the gas. It's the big particles that start to decouple from the gas. The gas, at the same time, is still viscously moving outwards, so the gas is still moving outwards.
Okay,
it
so
is also moving upwards because of the gas pressure, basically. So and some of it is actually moving inwards as well, because it's still, it's also still accreting onto the star. So it's a combination both accretion, infall, viscous evolution in the midplane outward, and also vertically. So the gas dynamics are complicated as well.
thank you.
Pressure, is it the thermal? Dust becomes anisotropic.
Yeah, so these are what we call optically thick disks, meaning optically thick to the UV radiation. So radiation pressure on dust is not important in this phase of disk evolution. That becomes very important in the debris disk phase, but that is not the phase that we are studying here.
Okay, Morelia, do you have any question?
Oh, is there any question here? I have one. I'm Aina Palau.
Yeah.
Ewine, you showed a transitional disk,
Yeah.
first observed with the SMA and then with ALMA.
Yeah.
and it was strongly asymmetric.
Yeah.
And I think it seemed that the ALMA image showed the peak of the emission like offset with respect to the SMA image.
Yeah.
I don't know if...
Yeah, that's a very good question. So this shows the importance of image fidelity. So Joanna Brown, who took that particular image of the SMA, always warned that, you know, the image fidelity was not high enough to say really whether, and if so, where there was an asymmetry in the dust distribution. So she could see sort of that it was not a smooth distribution, but she could not really, you know, with confidence say what the asymmetry is. With ALMA, the image fidelity is just so high that there's no doubt anymore as to where the asymmetry is.
Okay, thank you. Any other question? We are done. Thank you very much.
Okay.
Thanks for listening.
Okay, let's thank Ewine again. And remember, we have now after parties.
He put it down there.
Very nice. It's amazing, the resolution.